I think we can start. So, hi again to everyone officially. It's yet another webinar at Cloud Study Network, and today we have an amazing person with us and also a great company behind him. It's Andreas, and stage to you, Andreas. Feel free to introduce yourself. Tell us a little bit about yourself, what you're doing at this company, and a little bit maybe like what the company is doing as well.
Yeah, sure. Fantastic. Thank you. So I'm Andreas from Neo4j. Neo4j is the funny collection of letters that actually is a graph database. Maybe later during the Q&A, I'll give you some more trivia about Neo4j and the naming and its history. We're a graph database company. I work with the DevRel team. And the material I'm going to go through today is an introduction to Neo4j and really broadly graph databases and how to think about graph databases. I was just thinking about this and sharing a little bit with Karen before we started that I've been with Neo4j actually for about 10 years now and been doing these kinds of introductions and training courses with Neo4j through that entire time, through all the different roles I've had with Neo4j. And I've always loved this part of the journey, as it were, like the first introduction to Neo4j, whether it's live or if it's on conferences, or webinars or however it is, that I think back to like when I first encountered Neo4j, just the idea of graph databases and what you could do with them was exciting to me. I loved it. I fell in love. And having that possibility for you here, that I hope you through this next hour or so, that you get to understand like, what this idea is, like, maybe what you could do with it. And of course, it has very good practical purposes, but I've been drinking the Kool-Aid for 10 years now, not just because I work for Neo4j, but because I every day still love these concepts and like what I can do with these concepts and how it changes, the world and how I think about things. So I hope you have what I had 10 years ago, which is a graph epiphany, that the light bulb goes off and you're like, oh, graphs are pretty cool. I can see how I would use this stuff.
That's great. Thanks, Andreas. And yeah, we still have more people joining the call. Andreas, the biggest use case or killer application for Neo4j database, could you name one or like what happened in the recent times, maybe like a big event, maybe something where Neo4j was behind it?
Yeah, I'll get into some more details about it later, but like one of the most kind of broadly publicly aware kind of instances of graphs changing the world and making actually some nice social impact was when the ICIJ, the International Consortium of Investigative Journalists, used Neo4j to basically present the Panama Papers and then the Paradise Papers, these offshore data leaks, this huge trove of data about financial organizations and how they're set up and who's involved in them, that really provided startling insight into these kind of shell companies and who was involved. And well, a lot of it is good, but some of it is where also you find people trying to hide. And really, because it was one of the great kind of success stories of graphs, that like you could look at all that data sort of individually, and the classic thing to do is to follow the money. So this is a trail of following the money. And you could put so much data, you could put it all into a database and then you could follow the money. It wasn't just something that an individual private detective could do, like, working really hard with kind of a small amount of data. This is a huge amount of data that you could actually follow the money and find interesting things about. So the Panama Papers and Paradise Papers, I think, was our, if you've heard about graphs at all, you might have heard about it in that context.
That's great. That's just the use case to keep in mind for everyone and to just get intrigued about the whole technology behind it. And thankfully, Andreas will walk us through this whole thing, how it works exactly. So everyone, I would ask you to stay muted during the conversation unless Andreas asks a question, and then feel free to unmute yourself. Otherwise, we will have a question and answer session at the end. So yeah, Andreas, I think we can proceed. If you could briefly tell us about today's agenda, and you can already dive in. Thanks.
Cool. Sounds great. So here's the goals for this session together today. We're going to answer the basics about, okay, what is a graph database? Why do you even use a graph database? We mentioned the Paradise Papers as a well-known kind of public example of why you might want to use a database and what you could do with it. And we'll look through some other examples about where it's really applicable. On a practical level, of course, it's a database, so you might want to get some idea about like how you could actually query this database. And this is the last bullet is really a favorite thing for me to dwell on. It's like, how is this really transformative? Because I think there's this simple idea that is behind a graph database that changes what you do with data and what you can do with your applications. But also because you can do it on this large scale, changes how you see the world around you. Things that you wouldn't even bother trying to do before. You're like, actually, this is now possible because I have a tool that I could apply to these. So it can be quite powerful. Oh, and because as sort of a subtext here, let me go back for a second. This is part of our Graph Academy live series, the material that I'm going through today. This material itself will be available. Of course, the recording will be available. And the Graph Academy is Neo4j's own series of courses, so that if you want to go in deeper about anything that we're touching on today and actually take some courses and get to certification, the certification is absolutely free. You just have to complete the courses, actually answer all the questions, and then you can get certified as a Neo4j graph expert. So this material here is an introduction to the broader base of information you'll get at Graph Academy. I think it'll set you off pretty well. Okay, so what is a graph database? The first step, of course, is that it is exactly what you think it is. It's a graph plus a database. Put them together and you get a graph database. Going way back into history, our good friend, if you're not familiar with him, Leonard Euler, is one of our math heroes, I think. He's done so much for mathematics. One of the things he's done for mathematics is give us graph theory. And this illustration here is this sort of progression of illustrations is where he started and where he kind of created graph theory to solve this particular problem. On that left, there's this historical map of a town called Königsberg. And there's this kind of, parlor game kind of question around how could you cross through all the bridges of Königsberg? So there's 7 of them. Could you start anywhere within Königsberg and cross all of the bridges, but only crossing each bridge once? Is that possible? And you could try to approach that in lots of different ways. Leonard ended up, of course, being a mathematician, and this is a math problem, sort of went for the completely abstract, how do I actually represent what this problem is? And sort of removed all the detail of the streets as the kind of the first step of the process, and that's it there in the middle. And what you end up with is that diagram on the right, which is a network diagram or a graph diagram, where the land masses have now completely been shrunk down to just what we call nodes. And then there's just lines between the nodes. This is the classic representation of a graph visually, is just circles and lines that represent a graph. Each of those lines correlates with one of the bridges from the left-hand side drawing. And now you've abstracted away all the irrelevant information, and you can focus on just the problem, which is a problem of traversal. Like, can you actually start from any of those blue dots and go across each one of those lines without crossing a line twice? It turns out you can't. It's not possible. But graph theory was born as a way to actually solve this problem. Graphs, as a graph theory, went on for many centuries, of course, and proved to be useful in lots of different ways. Wasn't really used as a database. Well, actually, that's not quite fair. Early in the 70s, there were other databases that had sort of graph-like structures. There were network databases. There's been lots of different incarnations of this. And for us in Neo4j, we have what we call a property graph data structure, where for each of these blue dots, that's a data record, but also each of the lines themselves are also data records. And so as an information structure, as a data structure, graphs are really just a way of organizing those data records. That either the data records are nodes themselves, they're just sort of standalone, or they are data records that connect to something else. And you can map that to object-oriented if you want to, or to other models and of how to think about the world. But we talk in terms of nodes and relationships. We call the bridges or the lines relationships. And so here's what a graph would look like. You would give each of the nodes some sort of a designation. So here they've been given letters, each of the relationships have been given numbers. And having gone to the abstract math, you would then go back to make it into a database. You'd though go back and actually add information. So that's the property part of the property graph structure, where in addition to the mathematical structure of there are these things are connected, you can now store data there as well at each of these points. So each of the bridges we happen to know have names, and each of the land masses are basically parts of the town of Königsberg, either the north part or the south part. And so each of those actually have information as well. So you just take that graph structure, which presents how you want to organize the data, and then you can attach information. You can attach data to all the parts of the graph structure. And of course, keeping in mind that all of that originated with a map. Here's a more recent map of that area. It's still an historical map, but it's not a drawing anymore. And what you can then do is, so the 7 bridges problem was one problem. It was just about graph traversal, so it only cared about the data structures. But because you can add the information back, you can say, well, for each of these bridges, maybe there's a cost for crossing that bridge, and you could attach costs to each of those crossings. And maybe for each of the land masses, you at least know, the names, of course, of them. But you also maybe know the area, how big they are relatively, and so you could add that information. Any information that is relevant to whatever you're trying to do, of course, you can just add to the data structures, and then continue to do traversal-like queries if that's what you want to do. If you still want to do the 7 bridges, but now you want to keep the cost low, now you can add cost to part of the traversal. So you can say, okay, I want the cheapest way to get from D to B. You have 4 different, well, I guess you have all the bridges. You can cross any way you want to get from D to B. But what is the cheapest way to do that? You can now ask that question of the database. So that leads us into why you would actually use a graph database and the various applications of this approach. I think broadly it really does fall into 2 camps. That you independently have realized that the data you have has a graph problem, that the data is highly connected, and so you have a lot of relationships that you care about. Back 10 years ago when I first joined Neo4j, I was doing medical informatics in sub-Saharan Africa, and we were setting up the nationwide health information system for Zambia. And we realized we had a graph problem because we had to go between sort of high-level reporting about how things were going with individual patient care. And crossing through all of that also was having multiple languages to deal with at different levels for how you express what's going on and how progressions of diseases happen. So mapping between in-person care, what you're actually doing to help this person who needs your help, all the way through to abstracting it to what does the WHO want to know about what you've been doing to help people with various things that map into medical ontologies. That's when my graph epiphany happened. So I realized I had a graph problem, and I went and found Neo4j. So if you have some data set where you have lots of connected data, you might end up, of course, using Neo4j. You might use graph databases just if you realize you could be using a relational database. And certainly it was true in the early days quite a bit for Neo4j, and it still is true that people don't think they have a graph problem, but they just have a recursive query problem that either because of the number of joins you're doing or because the joins are recursive, that part of a data set or an application is slow. And so maybe you take just that part of the data and you put that into Neo4j, because doing queries that are based on lots and lots of joins, lots of dynamic joins, is easier to do in a graph database. So it's simply a performance benefit. Or if you're doing things that are very particular, of course, that are hard to express, like pathfinding, the original kind of 7 bridges problem, or doing dependency analysis, and then the list actually goes on and on about very specific graph problems. If you realize you've got a graph problem, then of course you would use a graph database. There's a subtle other aspect to it that isn't as common if people don't already understand graph databases, which is that it's simply a more fun way to work, I would say. And that's what the right-hand side here goes into a little bit, that it's more fun because there's less friction between how you already think about the world around you and also data and how the data is stored. So if you think even about ER diagrams or anything within data, it's natural for us to think about two things. we're really good at categorizing stuff. So this is a type of thing. But then things don't live independently. We also think about like how that thing, relates to other things around it. That's really what all data sets are about. So whether it's completely abstracted or it is real world, all domains are highly connected worlds. So the database stores the data exactly how you think about the world already. So you don't have to try to do any kind of mapping. You just kind of do what we say is, whiteboard design. And usually just exactly what you draw on the whiteboard is what you end up storing in the graph. I will add a caveat there that one thing that does end up happening is similar to kind of refactorings you might do with a relational database, where you change your schema. With a graph database, you might change the structure of the data as well to match the queries that you're doing, or because you've got new information that you want to add or new things you want to be able to discover. So there's still some kind of restructuring, rethinking about your problem space as you write queries. But mostly it starts off being pretty purely related to exactly how you think about the world. And this lets you then do all kinds of things really, which are part of the left-hand side, where you can, now that you have all this data in a graph, you can do very graphy things with it. And there's, again, less friction actually with what you think you want to do with how you do it, because somewhat it's true that if you can kind of express what you want to say or what you want to query the graph in terms of just a question, a spoken word question, that usually sentence that you might be asked translates very closely into the kind of queries that you would write. And we'll see a little bit of that as we get into more of the material. Okay, so just some fun examples. This is a very simple graph that, again, classic circles and lines connecting them. These have arrows. So we've on the outside here, we've got some people who have all bought this particular product. Here are trainers in the British idiom of calling what in America you would call sneakers. These are sports shoes. So these people have all bought these sports shoes at different points in time. So they've got timestamps about when they bought them. And this is a very small graph and very easy to understand, right? So this person whose name is Jane bought this product, which is of type trainers, for the price $89.99. And you can kind of read the graph and express these sentences. That aspect will come back, as I've been saying, that as you think about the graph and as you look at the data, you kind of can read it, and it becomes almost natural language sentences. You can fill in a little bit here and there to make it into sentences. And that also translates into how then you would ask questions, where you would just leave blanks, essentially. You think, well, I want to find out who bought this product. For this particular graph, you can also then start to elaborate on it and realize that it's not just that these people have in common that they bought this product, that you may not know beforehand, but if you're in a business, as many of us are these days, that's tracking social media and where people are communicating, you might realize that there's more relationships between your customers than are obvious by their buying patterns. So here, Jane might have tweeted about that she loves her new trainers, and you might realize that Allison actually is on her feed and that she's read that message. And then maybe as a consequence of reading that message on Twitter, she decides she's going to talk about it on Facebook. And Ian happens to actually be on Facebook. And you wouldn't have realized, or you may not have realized within just the product scope, the kind of consumer graph, that these people not only just bought this, but they happen to know each other, or at least be in the same circles on Twitter and social media. And so that's another dimension of the graph that you can easily just add. Once you find that information, you can just add more information. There isn't any kind of concerns about having an overloaded schema. One of the nice aspects of the graph is that as you get more information, you can continue to elaborate on the graph, and there's this kind of schema evolution that happens. We start from just a very immediate problem you're trying to solve, and over time, as more data becomes available, you find ways of expressing that data and expanding the scope. This then, of course, creates a very small graph still here, but it's useful in two directions. It's useful for making product recommendations, because now we know that these three people know each other. Have these shared messages that we realize creates a social network, which means that if Allison, for instance, buys another product, that we know that social influence is very influential. So maybe we would have some very specific targeted messages to when next time Ian logs in or Jane logs in saying, hey, Allison just bought these really great socks that happen to go well with those sneakers or those trainers. And then you can actually have better, of course, recommendations as a result of that, which if you do it well is a good experience for users also. It's not uncomfortable for them. There is of course this concern about users worrying that companies know more about them than they know about themselves. And we who work in data know that that is a reality, that when you have all of the data, you often know more about people than they are aware of themselves, certainly more about their circumstances and their relationships and the world around them. So finding the right balance of like letting people be in control of that information and also then being able to leverage that information for their own benefit, I think is a good approach to kind of find the right balance. All right, and the final step, of course, that Ian also happened to post. He posted that to Instagram. This is the use case that is more popularly known, that we brought up at the beginning of the session, the Panama Papers, which as a graph model was very simple, but the simplicity of the model isn't really the question. It was, even with a simple model, you have these powerful outcomes. And the model itself looks like this, where within the Panama Papers, which is based on this treasure trove of data that was gotten out of a law office in Panama, you had business entities, and then you had individuals who had roles in those entities. And of course, those individuals and those entities existed at addresses. And often they had, there's this sort of category of other stuff that was also included there. That's the blue circle over on the left. With this simple model, and you can see that this model is almost, it's richer in the relationships than it is in the individual entities. It's because those relationships themselves are really where all of the power came out of this data set. Where, again, if you looked at the individual nodes themselves, like there's an address, great. What does it matter that there's an address? What matters about that address is if this address is shared by the same officer and an intermediary and an entity. If they're all kind of at the same address, then okay, you know a lot more about them than they're involved in a particular entity. That you can triangulate and actually sort of reveal patterns within the data that show that even though people are trying to distance themselves maybe from particular things, you can look as deep as you want to. You can kind of recursively go through this as much as you need to find who's related to who, what entities are related to what other entities. And even if 99% of it is, in fact, 99% of it is completely legitimate and no problem with it whatsoever, it's the small percent which is fraudulent activity, or that has been set up to try to hide relationships, that is where all the power came out of the Panama Papers. So being able to look at that huge data set and then go through it to actually narrow down into like, where are the, who's trying to hide within this data set is what was fantastic about this. This going back a little bit more playfully to a simpler, friendlier kind of relationships. Roses are red, Facebook is blue, no mutual friends. So who are you? This was brought up a little bit in the product model, that often relationships between people in a data set that are seen indirectly. They're seen through something else. And so here's, for us, a classic data set that we like to use because it's pretty easy for people to wrap their heads around. This is a data set of actors and movies that they've acted in. And so it's super, super simple. There's just actors and movies. And yet, even with that, you can end up realizing that there must be relationships between these actors. They at least are aware of each other and know each other, even if they aren't necessarily friends. You at least know that they are co-actors. You at least know that, for instance, Meg Ryan and I don't know who's attached to the other end of her, Greg Kinnear there, both acted in You've Got Mail. So we know that they are co-actors. And even though that isn't a direct relationship within this graph, that's an emergent relationship that we can calculate within the graph and then also do reasoning based on that as well. So we can project essentially a graph that is a co-actor graph, and either materialize that by adding extra relationships, saying that we could draw a line essentially between Greg and Meg, and say that they are co-actors if that becomes an important thing for us, or we can simply compute it every time that we need to in sort of the classic computer science way. If you're doing something infrequently, you can just calculate it. If you do it a lot and it doesn't change, well then calculate it, pre-calculate it essentially, and then store it. So materialize a relationship if you need to, if you're going to do a lot of work with the co-actor relationships. Otherwise, just calculate them on demand. So here, Meg Ryan is a co-actor of lots of different people within this graph. You'll see Kevin Bacon over there as well, who is really the basis of another pop cultural game, the Kevin Bacon, the Bacon path between actors, like how many movies you have to go between to find Kevin Bacon. And surprisingly for most actors, it's not very many. He's been in so many movies. It's still true that he is very well connected in terms of co-actors. Okay, so what are good graph scenarios? Continue to elaborate on this a little bit. And these are just some questions to ask yourself that are worth considering, and that if they resonate, then maybe you have a graph problem, you have a graph data that you're not taking advantage of. So if what you're trying to do involves understanding how things are related, that is very much a graph problem. You should consider using a graph database for storing that data, and at least maybe analyzing that data, if not storing it as the source of truth. The product category thing that we showed earlier is a classic example of that. When we first started doing, this is called recommendations, when we first started doing recommendations sort of as a thing to blog about and talk about and present about, for us, this is just a simple query of the data. There are companies who have frameworks and libraries that do recommendations that are dedicated technology, and turns out that for high quality recommendations, it's really just a simple pattern matching thing within a graph. And if you just put your data in a graph database, that your recommendation engine can simply be a couple of queries. It doesn't need to be some custom bespoke code that you write. You can just do a graph query and find really high quality recommendations. So that same pattern turns out that the way that you do good recommendations is very similar to the kinds of pattern matching that you use for fraud detection, for finding duplicate information or perhaps redundant information, and for doing things like finding data lineage as well, where it's all about how are these things related, and let's make sure that we represent that because it's important for governance reasons or for whatever other motivations you may have. Similar, but I think a bit, sometimes maybe a bit more hidden, is when something is very highly self-referential. As maybe I tend to be very self-referential, I think about myself thinking quite often. So does the problem you're trying to solve involve a lot of self-referencing? Is it a lot of recursive queries? Sort of some classic examples of that are hierarchical data structures that, of course, you can materialize inside of a graph. So if you have, some company hierarchy, it's somebody who manages somebody else who manages somebody else. That's a recursive data structure. So that happens very naturally in organizations. Anywhere you have hierarchies, you have these kinds of data structures. In access management, so in identity and access management broadly, it's a huge thing where the overall structure of the data is very, very simple, but it is intensely relationship based and intensely self-referential, and like just these recursive queries that you end up doing. Obviously throughout social and any kind of friends of friends type queries are highly self-referencing, so that if you had all of that data in a single table, trying to run queries on a friend of a friend of a friend of a friend of a friend is possible. But as your data set grows, one of the hidden benefits of having it in a graph structure, it's as if a graph took that stack of people who might be friends with other people and just kind of unrolled the stack so that for every given person, they have direct connections to the other people that they are friends with. So rather than having to perform calculation to figure out for me, who are my friends, and then go calculate that and then go find them, once you found me, ABK, there are data structures that actually connect me to the friends. So there's no calculation to be done at that point, because Neo4j, the graph database, has essentially kind of pre-calculated the joins, if you would, so that having found ABK, you can just follow pointers to go find the friends of ABK, and then follow pointers to find their friends. So that's where one of the performance benefits comes out. So if you're doing a lot of queries, and if you took all of that data structure and collapsed it back in, trying to do those self-referencing queries involves a lot of computation. Instead, you can optimize it by reusing it in a graph database. And similar to that, if the relationships you're following, this is, of course, the theme, it's all about relationships. If you're exploring relationships and you don't know where you're headed, you don't know if you're just finding friends of friends, you're just like, okay, I've got this thing and I've got this other thing. How are they connected? Are they even connected? That is a graph problem. That's a very, very hard problem to solve with anything else. It's a very natural thing to solve with a graph database. So if you had this sort of structure here, which is like a supply chain structure, doesn't matter if it's a supply chain, the logistics, bill of materials, network management was one of the big early use cases for Neo4j, where if you had, a nationwide deployment of telecom equipment, and you were like, oh my gosh, this one power transformers, just blew up. Which customers have been affected by that? It's a really hard problem to solve if you don't have all of the data represented in a graph, so that it's just, in addition to the physical information, you have also the logical information, so that you can build out the entire, kind of dependency tree of what ends up being affected when this thing disappears, what was attached to that thing, so you can know before the customers come to complain to you. You could even be proactive and say, hey, we know you're about to lose service, or you did just lose service. We're sorry about that. We've got a truck, headed out there to go fix the problem. You'll be back online in an hour or whatever it might take. Those kinds of problems where if you didn't know beforehand, you have to just kind of, from a given point, fan out and figure out, what's related to that point, is really great for a graph database. And whether it's fanning out or it's lots of different alternatives, this is a very simplified version of the London tubes stops. If you want to find different routes, I guess also back to the Seven Bridges problem a little bit. It's not just a question of like, okay, how do we get from here to there, but like, what are my different options? So this is a very classic graph problem. It's obviously very relevant for mapping, but it turns up in lots of different non-map, but map-like, I guess, topologies, I would call them, where you care about not just a path, but all of the potential paths, and then being able to have alternatives. So whether that's for doing routing itself, or if you're doing infrastructure management or dependency tracing, this is a very natural thing to do with a graph database. Okay, I can't see your faces. I'm going to assume everybody is just thrilled with this and think, okay, this is really cool stuff, but how do I actually do this stuff? So graph databases, those are the ideas behind them. Those are the kinds of things you might want to do with a graph database. Practically, what does it look like to use a graph database? And this whimsical note here is like, walk like a patternician. It's all about thinking in terms of patterns. It is really fundamentally what it's about when you're querying a graph database, that if you can express what you're trying to look for as a sentence, then quite often that sentence translates right into what the graph query itself would look like. And there are two aspects of this that would be useful. First, of course, the foundational part is remembering that the data structures you've got to work with come in two parts. There's what we call the nodes. Those are the fundamental individual data records that are the things really most often within the graph. So the main data elements within the graph, whether it's people or things like vehicles. And then there are relationships. These are the two big data structures we care about. Nodes and then relationships, which are pairs of nodes, and then extra data that you can attach to that pair. The relationships always have a direction. You can ignore the direction if the direction doesn't matter, but the direction always exists. And they always have a type. So you can have you can have a node living by itself, but you can't have a relationship without having nodes on both sides. There's no such thing as a bridge to nowhere within Neo4j. Does not make sense. That's an important concept, because it's also ends up being a problem for data integrity. That for Neo4j, one of the reasons we've always been an ACID compliant database is that losing part of a relationship is catastrophic for a graph. That much of the logic of sort of the business rules you might have around the data set breaks down if a relationship has been compromised and like one end of the relationship is no longer there. There's a bit of corruption that happens in the data set that tends to propagate, actually. This is what we've found in various use cases. Because of that, and from the beginning, Neo4j has always been ACID compliant, so that if a relationship has been committed to disk, it's been transactionally committed, you know that it's there, you can make you can reason on that predictably and grow the graph around that without any concerns. The reason we know that it becomes a problem is because other graph databases and even kind of emulating graph databases, you can also do that. There's lots of, you can in the same way that we as data scientists and computer scientists know that you can take any given data model and approach and language and apply it to lots of different things. You could do graph-like things in a relation database, for instance, but not having it in, if you don't have it in something that is dedicated to graphs, you can end up with some corruption that occurs. So our customers, I guess I should say, sometimes have learned that the hard way and come back around to Neo4j to have the nice security of having transactional graph operations. Okay, so we've got nodes, we've got relationships. So this person happens to own this car. The relationships always have a relationship type. For the nodes, you can also add labels. So for the relationship type is mandatory. They always must have a relationship. You can't have a relationship that doesn't have a type designation. But optionally, on the nodes, you can add labels, multiple labels. Classically, people start with typed-like labels, so a person and a car. You can add as many labels as you want to for whatever purpose you think is appropriate. The way to think about that is that a label is really a way of grouping or associating a set of nodes. And so if you want to identify subsets or cross-sectional sets, you'd use extra labels for that purpose as well. And that lets you end up having different ways of slicing the graph, I guess I would say. You could have kind of different cross-sections of the graph based on the labels and the relationship types. And once you've got that, that's the basics of kind of doing the data structure. To both the relationships and the nodes themselves, you add properties, where properties are just key value pairs. And they're simple key value pairs, numbers, strings, arrays of numbers or strings, that kind of thing. Okay, once you've got the data structure all set up like that, to do the actual querying, we have a query language that we call Cypher. Maybe later in the Q&A, we can get into some trivia about that as a name. But Cypher is fundamentally a pattern matching query language that was built for graphs. It's declarative the way that SQL is. Of course, it's expressive, and it's all based on pattern matching. Somewhat playfully, it is based on ASCII art. Very genuinely, it kind of arose out of our own interactions around Neo4j when we were developing the database and we were designing a query language. We realized that we had conventions established for chatting with each other or sending emails with each other for how we would talk about graph structures. And we essentially just codified those into what became a query language. So that if you had a very small graph structure like a person whose name is Tom Hanks, and you wanted to find that, well, we talked about that as being a pattern match that you wanted to do. And so we have the match clause within the query language to say, okay, we want to match this pattern. And the pattern that's presented here is got some parentheses around the letter N. And the N here ends up acting as a variable that will be bound to all the results of that pattern. And it's in parentheses because parentheses are roundish. And so that, seemed like the right way to represent a node. So match nodes that are anywhere in the graph. So there's no other qualifications right now. Just match all nodes and return those ends. So no matter how big your data set is, this will get all the nodes. If you have a few million nodes in your data set, this is a very easy query to write. That is probably not the best query to write because you'll get the entire data set back. If you want that, great, but be prepared for the stream of data. If you want to constrain that data so that instead of finding all of the nodes, you only want to find the nodes that have been labeled with a label called person. A little bit like type annotation, you still use that same pattern of a single node in parentheses, but now use this colon person after the colon. That is the name of a label that you're looking for. And so now this will still find that single pattern, single node pattern, but now it's being qualified with nodes that have the label person. And now you'll just get all the people, so you won't get any of the movies if this was the movie data set. We can continue to elaborate on that to add more information to qualify the pattern. If you want to look for specifically Tom Hanks, you can use the kind of bracket notation for doing somewhat object literal-ish record specifications. So that inside of the squiggly brackets, we say we want a name colon Tom Hanks. And so now we're looking for all n's colon who are persons who have a name Tom Hanks. If you have more than one Tom Hanks in your data set, you'll get more than one Tom Hanks. But if Tom Hanks is unique, you'll get just the one data record. By returning n, you'll still just get everything that qualifies. So this works specifically for exact matches. You can inline all this information, and it's very compact and it's expressive. I want to match all the persons whose name is Tom Hanks. It's a bit awkward right there, but like it's almost like reading out loud exactly what you want to do. And this only though works for exact matches. This will only find Tom Hanks, not anything else. As you'd expect, as an SQL-like language, Cypher also has a where clause, so that you can add predicates to the query, so that in addition to the pattern that you're describing, you can then add extra predicates for qualifying different parts of that pattern. So if here we captured instead of an n, we've switched to using p for the person, and then in the where clause we say we want to find p.name equals Tom Hanks. The result will be exactly the same as we did in the first formulation when we had Tom Hanks inlined, but now it's in the where clause. And then if you're adding multiple predicates or like having more complex predicates, then it makes sense to break it out in the where clause. As an example of that, if we're, instead of looking for persons, if we're looking for some movies and we cared about the movies that were released after 1990 and before 2000, so just that decade of movies, you could just add that as predicates into the where clause and of course get those movies back. So a bit bigger example within this movie graph, which is one of our data sets. If we had movies with titles and we knew when they were released, of course, actors with names, let's look at what we can do for more complex patterns. So we started with looking for just Tom Hanks, but if we also want to find all the movies that Tom Hanks acted in, if we were saying that as I just did, we'd say, okay, for a person named Tom Hanks who acted in some movies, that's the query you would write. We still have the round parentheses for person. So parentheses person named Tom Hanks, that's a node Tom Hanks that we're looking for. And then there's a relationship here, which has got two things going on at once. It has kind of this dash on both sides, and then the angle brackets, of course, for forming an arrow. So it's from Tom Hanks, an arrow out, and then the square brackets is qualifying that arrow. So it's saying, okay, for relationships, this arrow, square brackets that have the type acted in. So from Tom Hanks, follow the acted in relationships to all of the movies. We've also given a label on the other side. And we only care about, even though we're looking with Tom Hanks, we already know about Tom Hanks. We don't care about him. We want the answer, which is the movies. So we've given that an M to be bound to all of those results within that pattern. And then for all those M's, return just the titles. So we'll get all of the movie titles for Tom Hanks. Taking that and extending the pattern a little bit, if we did want to do the co-actors that we talked about earlier, The co-actors just extends that pattern. You just continue to describe for a pattern where we want to match a person whose name is Tom Hanks in some movie with somebody else who's acted in that movie. Now here we've dropped out the acted in for Tom Hanks, both because of screen size, but also to make a separate point where here it's not actually just co-actors, it's any relationship that Tom Hanks has with a movie. So whether Tom Hanks has acted in that movie or he's directed that movie, if in this first relationship here, which is just dash dash angle bracket, because we haven't specified a relationship type there, any relationship can satisfy this part of the pattern. So acted in, directed, if he happened to review, I guess, a movie, whatever else happens to be in there, we will find those relationships to that movie. And then specifically, we're looking for people who have acted in those movies. So we're going to call them the co-actors and then return all the co-actor names. So people, so a person named Tom Hanks who has a relationship with some movie where other people who have acted in that movie are co-actors. Give me all those co-actor names. Okay, that's really just a taste of Cypher. There's an entire Graph Academy course, and also we do these in-person kind of sessions as well around Cypher. There's a lot more to Cypher as a language. It is now becoming an ISO standard, being called GQL. And the ISO GQL committee working group is hard at work formalizing a lot of what we have in Cypher, expanding it for interoperability and compatibility with SQL on different levels, and extending it a little bit in different ways also. It is a rich, rich language that is going to be pretty exciting and have a long life. We are hugely gratified to have the ISO effort kind of formalizing what we've done with Cypher. Cypher was awesome for Neo4j. It is even more awesome if it is useful for more than just Neo4j. If it is a general purpose graph query language, GQL, that is fantastic. That's great for us. I think it'll be great for all of you as well. If you learn Cypher today, the things you learn will be applicable for the next couple of decades, the same way that SQL query capabilities are still valid, will continue to be valid into the future. How is all of this stuff transformative? Going back to where we started here, and a graph database is simply a database which organizes data using graph structures. That's practical, that is powerful, and it, for me, my experience was that this unlocked a lot of approaches that I wouldn't have taken because I just had an intuition that they wouldn't work, I guess, with the databases that I had been using previously. When I had my graph epiphany doing the medical informatics, we had this crazy, ridiculous schema that we'd come up with to be very flexible and dynamic for capturing all kinds of different things. And you know, we'd realized, I had realized that we had encoded a graph inside of a relational database with a flexible schema, and it was terrible. It was not deployable. We ended up kind of really reducing what that schema looked like, trying to really simplify it so that it was useful, because we weren't able to use Neo4j for that particular purpose. We were still, you know, we were contract bound for actually using a relational database, and so that's what we did use. But it created the opportunity for me to learn about graph databases, and like a Neo4j would have been so much better for that. It would have been so much more powerful for that. And I realized that what I wanted to do was limited by, which is always true, right? You're limited by the capabilities of the tools you have, and we, you know, have some amount of confirmation bias that, you know, we shape our solutions based on what we know is possible, because we don't want to waste our time doing things that we know aren't going to work. But realizing that you now have a tool like Neo4j or in graph databases to actually change what's possible, it opens up all kinds of new ways of thinking about the world, either practical problems that you have, but also it affects a lot of how you think about things that aren't database oriented and aren't data oriented. This focus orientation around relationships, that what really matters is how things are related, and thinking about those as first order concerns rather than secondary concerns is really transformative to me, philosophically on a more personal level. Certainly practically on a database level as well. Though graph database is simply optimized for working with connections and data, and I certainly argue that all data is connected. There are subsets of data that are not connected. Like if you have, for example, if your primary concern is capturing sensor data, whatever the sensor is, temperature or something like that, whatever you happen to be gathering, and you just have this giant stream of data that really fits best inside of either a column store or some kind of a log, then that is not in isolation itself a graph, but how that data is related to other data is interesting. It always is connected. The reason that the data matters is because it has a connection with something else. So the individual records might just be essentially a stream of data, but that data set itself is related to other data sets, and that's where the interesting things come into for graphs. More natively for graphs, if you have people, of course, you definitely have relationships. That's the most natural thing. All applications that have any kind of social aspect to them, whether they are users or customers or whatever it might be, that's a graph. Having graphs for that part of the application is fantastic. It's a huge superpower. If you've got places, if you've got rows, of course, geospatial is a classic example of graph databases. If you've got messages, you've got replies, that forms an entire network where there are hidden communities that you maybe wouldn't see from exact relationships in other ways. In organizations, we often realize that the kind of departmental organization is one aspect of how people are related, but the kind of messaging paths are the more real structure of the organization. So, there might be two people within an organization that communicate quite a lot, but that are in completely different departments. That is a classic scenario and a good one, right? But something to be aware of, that that's those relationships that aren't explicit in the organization are as important to both cultivate and support and recognize as the more explicit who works for who kinds of relationships. Sometimes that just shows up in the messaging. If you've got transactions, or transactions themselves are relationships, they are not isolated things. They are a relationship between people partaking in the transaction, the thing itself being exchanged in a transaction. All of that matters for relationships. Pretty much if you have things, you usually have things, connections to other things, and those things have connections to other things, either within themselves to other things. Really, one of the challenges I think ends up being that what does the edge of the graph really look like? And trying to maintain focus on exactly the problem at hand is a graph modeling challenge, where you could add as much as you want to, and the richer the data is, the more powerful the data is. But where do you stop? Do you connect it all the way to the the formation of the universe? Probably not. Somewhere earlier than that, you cut off okay, that's the extent of the data set that we're going to address. But generally, if you have data, you can always either recognize the relationships that exist or add relationships to it to have richer data. There's almost nothing that I think wouldn't benefit from a graph database. So once you have connections, you have new ways to understand, discover, and enrich the data that you already have. Yeah, this is, I've never seen this not be true. I've yet to have a conversation. Actually, right, going back to the time series. Time series is the place where it's not true, because you don't, in that particular instance, there aren't connections there, except that layering connections on top of how that time series is related to other things is really what matters. There's always connections available, and if you have those connections, you should capture those connections and use them. Okay, I'm going to stop there. These slides are available. Thank you for sitting through this session with me. I'd love to take however much time we have left, and I'm available as long as we want to run to talk through this stuff. If you guys have any questions, feel free to unmute and just go ahead and talk to me.
So thanks a lot, Andreas. It was an amazing presentation. It kind of Yeah, it changed one's mind, basically. It's another way to represent data. We developers usually are pretty much used to SQL or SQL, how you say. There is no SQL kind of approach, you know. It's kind of easier. You don't have to like design the whole thing very much. You can just throw the data into it. But like for particular use cases, or tell me if it's if maybe you can use it like almost for everything, like for all data types and data representations. But this graph database, I know not. I'm not wondering why the guys who did research into the Panama Papers and stuff like this use this platform or this database to represent the data. So it's really very powerful, and I guess the power of it lies in the querying at the end. You know, like so you have to save the data in appropriate way, but then as you try to query it, this is like where the power comes up. You know, like it's a easy way to build queries. I see it's like it's also a really interesting like way how you put it with this Cypher, which seems like going to turn into graph SQL, or how is it called, like
GQL.
GQL? Yeah, that's really interesting. Amazing. Thanks a lot.
Cool, good. I'm glad to hear all of that. Yeah, you remind me that there's a classic Steve Jobs quote about computers being sort of a bicycle for the mind, where he meant that, you know, once you start being able to use computers and people have personal computers, that they let you go further than you would have been able to go by yourself. And I think that's true of graphs, that graphs let you kind of do things with more data in a way that you naturally do yourself anyway. And so you suddenly have a tool that thinks and works the way that you think about the world around you, and it extends what is possible. You know, if you have conspiracy theories about the world, okay, it doesn't have to be a theory. Capture all the data and look at it, and you'll be able to decide whether or not there's truth there.
Mm-hmm. Yeah, great. We actually have a question. Can you, Andreas, look please into the chat?
Yeah.
We have a question from Vijaya.
Are nodes unique? Are they like primary keys in a relational database? Hey, yeah, great question. So this is one of the classic challenges, I guess, within a graph database. So in terms of relational databases and NoSQL and then graph databases are schema-free the way that NoSQL is, but you can add some schema constraints to it. So uniqueness is one of the things you can do. Nodes themselves are individually addressable. So when you create a node, it has an ID. So you can talk in terms of that ID, and that's great. But that's not really a primary key. A primary key, of course, as you know, is a domain-related thing. You can then add properties to the nodes, and then those properties can be guaranteed unique within the scope of a label. So if you had persons and you had you know, some person ID, you can ensure that that ID is unique, and then use that as a primary key. And from Daniel, just a question, understand that the power that this offers is the fact that you can relate all that data that you have in nodes through the relations between them, but from an infrastructure point of view. Yeah, okay. How do you distribute this? How do you distribute the different Neo4j instances in a way that you end up with a huge data set in a single location? So are you asking about sort of data partitioning? Possibly, Daniel. I'm sorry. Could you clarify? Or do you mind unmuting? Yes. Data partitioning. Okay. Yeah. So data partitioning is an incredibly difficult graph problem. It is something that we have been taking different approaches to for as long as I've been with Neo4j. So for at least 10 years, we've had a continuous background thread on data scaling and data partitioning particularly. And the hard part about data partitioning is there's no good way to do it with a graph because everything is connected. And so every time you do it, you really want to do it across a way that matches data access patterns, so that for any given data access, you're only accessing one part of the shard. If you have data queries that run to a particular shard and then branch off to another shard, those queries are going to be not terrible, but they're not going to be great. So the upside of sharding is that you get distributed data sets, so you can actually partition stuff, and you can get multiple hard drives, and maybe some cost benefits there and other things. Also, you maybe get some write benefits there because you can write to multiple things at once. The downside is doing queries. So we have something called Neo4j Fabric, which is our current approach to that. And Fabric essentially takes not a partitioning view, but like a joining view of graphs, where rather than taking a giant graph and finding the right place to slice it, Fabric says, okay, identify multiple graphs that you want to bring together into one query space. And then we have queries that you can run that you can then run across that query space, so to the individual graphs, where then can actually pull everything together so that you know where the boundaries are because you created the boundaries. And it's not about taking one monolithic data set and breaking it up. It's about taking multiple data sets and finding a way to bring them together. It still has that performance challenge that I mentioned, because you're going to be, every time you ask a question of multiple services, then that'll be slow. And also the queries right now individual queries cannot cross the subgraphs. So you ask multiple subgraphs and then you kind of figure out an answer based on that. You can't ask a single subgraph and have that question also cross into another subgraph. You can't have sort of peer crossing in that way. That's still something that we're working on solutions for, but we don't have a good way to do. If you simply want to do the data partitioning part, though, that is one approach to it. And if you have data that is naturally partitioned in a way that you're not worried about having to query across the partitions, so you have a North American data set and a European data set, and yeah, okay, sometimes the data crosses, but most of the time it doesn't, then that's a really good approach.
And we have one more question here from Surjit. If you could scroll a little bit up.
Oh, here we go. How do you decide which way a relationship should be directed? A product belongs to category or category has product? Yeah, so that is a great question. And I don't have a hard rule there. I think the best way to structure that is the way that you tend to express it yourself. That the best way to write relationships and labels is based on how you would just have them in casual conversation. So that if the way you think about it is, as your example here, if you think about it more in terms of that this product belongs to a category, then that's the direction you should do. That's how you should express the relationship, and also how the direction should go. So the direction should match the language you use on the type. So whether the product belongs to a category or the category has these products, going out the other way. So for that specific example, of course, I don't like personally. My preference would be for the belongs to category, but only if the product tends to belong to a single category. So if it can belong to multiple categories, then I personally find it confusing because I like my things to be highly hierarchical in terms of categorization. I don't like things that belong in multiple categories. That just messes with my head too much. So I would opt for the second option, which is the category has product. But it really depends on the kinds of queries that you want to do. Similar to how you think about relational databases and relational schema, that's not just how you set up the tables, but also the names you give to the tables and to the rows and everything else. That the naming you give should really reflect the kinds of queries you want to write, because that's going to help your kind of developer productivity later, remembering how things are structured, because you're going to be led along those paths.
Great. And we have a let's take a last question here from Gino. The question is, when we are working with highly linked data, how do we handle real-time updates from multiple locations across database replicas?
Right. So as it is today, so Neo4j is transactional. So if you have real-time data, it depends what you, of course, mean by real-time. Like if it is sensor data that is streaming, 1,000 sensors streaming 1,000 pieces of information at once, that's probably more data than Neo4j can ingest. If it's users that are writing messages, if it's human scale real-time rather than machine scale real-time, then you can do that. And you just let Neo4j take care of it. Neo4j takes care of the transactional rights. You don't have to do anything extra on your side. If you want to scale that up, then that would be one of the reasons to actually think about something like the fabric, where if you have multiple databases, you can parallelize writing, because now you have multiple things that can, because writes, I should say, if this wasn't, no, I'm sure I did mention it before. So with Neo4j, writes are always serialized because that's part of the transactional nature of it. It is a single graph with a single point of writing. So it doesn't matter if you have lots of scale out in terms of readers, that's really great. Even if you have a cluster that is managing the core commits to disk, it's essentially single streamed writes. And so you're limited by whatever the actual disk speed is for how quickly you can write. So if you have a lot of writing to do, if it's high volume writing, you're going to want to have multiple writers, which means multiple graphs that you can write to at the same time.
Okay. And Andreas, I heard that Neo4j now has a managed version of it. It's like SaaS or PaaS, however you call it. Is it the case? And can you just like say a couple of words how it goes? Like what's the entry plan? What's the capacity there in case if someone wants to give it a try without even installing the whole thing?
Yeah, thanks for bringing that up. I mean, so we do have something we're calling Neo4j Aura, which is our cloud managed service for the graph database. Aura has everything from a free tier for just trying it out and seeing what you can do with Neo4j, onto professional tiers, and then all the way up to an enterprise tier. The cost on the enterprise side goes up quite a bit. It's much more affordable. And I don't want to talk about pricing. You can go look on the website for the pricing, because this video will live longer than whatever pricing I quote. But you can look at the website to find out the pricing for Neo4j Aura. And it's a great place to just check out Neo4j, because you can just get a free database, try it out. We have both Aura itself and also something that predated Aura called Neo4j Sandbox, which has a lot of data sets already kind of built in that you can just start them up. And you've got 3 days, you can just do whatever you want to with them to kind of learn about Neo4j and learn about the graphs. If you take the Graph Academy course, that also ends up partly using Neo4j Aura for just spinning up databases that you use while you're doing the course. So that's a great way to learn, and without having to download, install, provision anything yourself, you can just use the Neo4j Aura service.
What's the capacity of the basic tier, of the free tier?
Yeah, the free tier is data record limited. I believe it's around 50,000 nodes, and maybe it's 150,000 relationships. Relationships are always more than nodes.
That's pretty a lot. That's a great way to get started with the database, with the graph database. Okay, so thanks, Andreas. Thanks everyone for taking time and visiting this session today. I will distribute a follow-up email where you will find a link to the recording. If you're watching it as a recording, you will probably find everything in the description of this video. Otherwise, there is again, as mentioned at the beginning, there is a free certification. It's always free. It's available on the homepage, from the homepage of Neo4j, but I will make sure to insert the link, direct link to the certification as well into our follow-up message. So after this session, you should have like enough information and knowledge to at least attempt and hopefully also pass. If not, you can attempt it as many times as you wish. It's free and it's not limited by the attempts. Yeah, it was really nice, Andreas. Again, thanks a lot, and hope to see you another time as well in our community.
Great. Thanks for having me today. Good to see everybody.
Thank you. Take care, everyone. Bye-bye for now.
Thanks, guys. Thank you. Bye-bye.
Bye-bye.
Bye-bye.